Murli sir, good afternoon. Murli sir, namaskar. Am I audible?
Yes, sir.
Okay.
Where should I start?
No issue, sir. You can off the video. Once we'll start, you can off the video. No problem. So yes, Kuldeep, I think, sir, we can start now, na? Are you ready, sir? Okay, you can start.
Welcoming Dr. MuraliKrishna H, an assistant professor at MIT Manipal. He has submitted his PhD thesis at IIT Mandi. His research areas include machine learning, spoken language identification, speech processing, and signal processing. Today, he will be sharing his insights on the practical aspects of speech processing. Let's explore the realms of knowledge together with him. Over to you, sir.
Sir, your voice is very slow, sir. It's very slow, not audible, I think.
Am I audible now?
Yes, sir. Now it's perfect.
Clearly, right?
Yes, clearly.
Thank you. Thank you for the introduction, and thanks Dr. Satyaprabhajan and other organizing committee members for inviting me here for this workshop. It's really my pleasure to talk to you all and interact with you all. I can see good number of participants here. So the topic for this session is introduction to speech processing and some applications of it. So I'll just share my screen and I'll switch off my video. Maybe that will be better for saving the bandwidth. Is it okay, sir? I'll switch off my video.
Yes, sir. I'll also switch off. Yes, sir.
I'll share my screen now.
Yes.
Is it visible?
Sir, visible, sir.
Yes. Yeah. So thank you. So as I was saying, the topic for this session is introduction to speech processing and applications. So specifically, we'll be discussing these topics. Initially, we'll be seeing some basics about speech signal. What are the different information carried by the speech signal? How speech signal is produced in a human being, because that is very much required for understanding the signal processing concepts related to speech processing. And then we'll see how speech signal is perceived, or how do we hear the speech, or how do we understand this? And the MFCC feature, the commonly used type of feature vector, type of feature representation for speech processing applications, and some applications. So if you have any question or anything to ask, you can just raise your hand, and or you can interrupt me in between. So I'll be happy to answer all those questions. Okay. So basically, the speech signal is an acoustic wave. Okay. So what do you mean by an acoustic wave? So I want this session to be interactive session. So we can just discuss. I'll just ask some questions. You can give your answers. That may be right or wrong, no matter.
Yes,
just give your answer and please participate.
The session should be interactive, as sir saying. Sorry, sir, interactive. So kindly interact with the sirs, okay, during the session. Thank you.
Yes. So what is the difference between an acoustic waveform and an electromagnetic wave? So I just said that the speech is an acoustic wave. the question clear? The speech signal is an acoustic wave and it is different from your electromagnetic wave. So I hope you have already studied this electromagnetic wave and acoustic waves to some extent at least. So what is the difference between them?
Sir, your voice is somewhere lagging sometimes. Your voice is.
Sir,
Yeah.
acoustic wave requires medium for propagation, whereas EM waves doesn't require any medium for propagation.
Right. So that is the correct answer. So the acoustic waveform, it requires a medium for propagation. So if you would consider the normal environment, the room environment, so medium is the air. So the speech signal, it travels in the form of compression and rarefactions of the air particles, whereas electromagnetic wave does not require any medium. Okay? And also the speed at which the acoustic wave travels, that is very less. So what is the speed at which usually the acoustic wave travels in room temperature and room environment?
Somewhere around 300 km per second.
330 meters per second. It's not kilometer. It is around 330 meters per second, or maybe 350 meters per second. Whereas electromagnetic wave, it is around 3 into 10 power 8 meters per second. Okay, so there is a huge difference. So that basic understanding should be there. What is the difference between acoustic and electromagnetic wave? Okay, so now just consider a speech sentence or speech utterance, which is given in the bracket. Like, this workshop is organized by KIIT. Okay? So if I consider this speech sample, which is an utterance or which is a sentence saying that this workshop is organized by KIIT. So what are the different information that is present in this particular sentence? What are the different information you can get from this sentence?
The name of the institute, KIT, and the workshop where the workshop is being conducted.
Yes. So that is the verbal meaning of the sentence, right? So
Yes, sir.
we're trying to understand what is the meaning of that.
Sir, you need to increase your audio.
Okay.
You are not
So
audible.
that is the verbal information you are trying
Yes,
to
sir.
get. So am I audible now clearly?
Yes, sir.
Okay. So please let me know if there is any issue with the audio. So first information what we get from the speech sample by listening to that is the verbal meaning of that sentence, right? And any other information can you get from this speech sample? Any other information? Can you understand whether the speech sample is belonging to a male speaker or female speaker, or maybe a child?
No, sir, not.
Just by listening to a speech sample, now you are not seeing me, just by listening to the speech sample, is it possible to recognize whether a speech is belonging to a male speaker or female or child?
No, sir, not quite possible.
Most of the time, is it possible or not? Can you just, if I just play audio from child, small child, will you be able to understand that it is a speech from a child?
Yes, sir.
Yes. If I play an audio from a female speaker, a typical female voice, will you be able to understand that it is a female voice at least? We don't know who is the speaker. That is okay, but at least it is differentiate between. You'll be able to differentiate between male and female speakers just by listening to voice, isn't it?
Yes.
Yes. So we can get information about the speaker also. So first thing is the verbal meaning in the speech. What is the meaning of that sentence? So that anyway we are getting. Second thing, we can get some information about this speaker who is speaking. In case you know the speaker already, just by listening to his voice, you can recognize him, isn't it?
Yes,
If
sir.
I play the audio from Narendra Modi, or maybe Virat Kohli, or maybe Amitabh Bachchan, so just by listening to that voice, you will understand that, okay, this is voice from, is this speech sample from Amitabh Bachchan, or maybe it is a speech sample from Narendra Modi, isn't it? Right?
Yes, sir.
So this is called speaker recognition. Okay? So given a speech sentence, first thing we can extract the verbal meaning of the speech. Second thing, we can extract or we can understand who is speaking. So that information is also hidden in the speech signal. Apart from that, this speaker and verbal meaning, any other information can we extract? Any other information just by listening to speech?
Intonation.
Sorry? Yeah, there was some answer. Can you just
Repeat the answer again.
Intonation.
intonation? Okay. Can I just convert, say that it is emotion of the speaker,
Yes.
right? So if a person is happy, the way of speaking will be different. If the person is sad, the way of speaking will be different. Or if he is angry, he'll be the way of speaking will be different. That means we can recognize the emotion of the speaker just by listening to speech. We can understand his emotions, right? So emotion is also hidden in the speech sample. Apart from that, if a person is having cold or some health issues, will that be reflected in the speech?
Yes.
sir.
Normal person speech and person having cold, will you be able to differentiate?
Yes, sir.
Yes.
Yes, sir. Clearly we can differentiate, sir.
Yes. So the health status of the person is also, we can extract that using the speech sample. Most of the time, there can be exceptions. I'm not saying every time we can identify what is the disease or what is the issue, but most of the time we'll be able to understand that, okay, this person is having some health issues related to cold or something related to his nose and mouth. Okay? And also, we can identify the language in which the speech is spoken. In this case, the sentence is, this workshop is organized by KIT. So obviously the spoken language is English. Same information can be delivered in any other language also. You can deliver this information in Hindi also, or maybe Odia also, or maybe Telugu or Kannada, whatever it is. So just by listening to speech, we can understand which language it is. So these are the different information that is hidden in just one sentence of speech or just one utterance of speech. The verbal meaning, the speaker who is speaking, emotion of the speaker, health status of the speaker, and the language, right? Is it clear?
Yes, sir.
So if you are trying to extract what is the verbal meaning of the speech, then we call it as automatic speech recognition or ASR. Okay, so it is automatic speech recognition or simply speech recognition, where we are trying to extract the meaning of the sentence, or sometimes higher end we also call it as natural language processing, but that for time being, let us take it as automatic speech recognition, which is the basic thing. And if you are trying to identify who is speaking, then that is called as speaker recognition. In speaker recognition, actually there are two things. One is speaker identification. Second one is speaker verification. Am I clear? In speaker recognition, there are two things. One is speaker identification. Second one is speaker verification. So what is speaker identification? Now I have already given the information that there are some set of n number of speakers. Maybe again, Narendra Modi, Virat Kohli, Rohit Sharma, and Amitabh Bachchan. A set of 4 speakers. I have already told you that there are four speakers, and I will give you one speech sample. just by listening to that speech sample, you need to identify who is the speaker. Okay, so that process is known as speaker identification. Just by listening that speech sample, you need to identify the speaker. So that is speaker identification. Beforehand, you know who are the speakers that are possible in the set. Okay. Now, second thing is speaker verification. So it is something related to your biometric. Okay, where just voice you are using it as the biometric feature. Let us say someone is claiming that he is Amitabh Bachchan and is trying to mimic the voice of Amitabh Bachchan. Now the system has to verify whether it is really Amitabh Bachchan or not. So that process is speaker verification. Okay, so this speaker verification can be used as your unlocking facility in your mobile phone or smartphone. Okay, it is already being used as an additional feature, additional security feature. Okay, so third thing, the emotion of the speaker. If you are trying to understand, if you are trying to extract the emotion of the speaker, then it is called as emotion recognition, right? And then health status, if you are trying to extract from the speech, the field is known as voice pathology. And if you're trying to extract the language, if you're trying to identify the language from the speech, it is called as spoken language ID, spoken language identification, or LID. Okay, so all these 5 different areas, they are very vast areas. Lot of research has been already done in each of these areas, and still so many problems are still open in all of these areas. Okay, so if you are interested in speech signal processing, you can pick any of these and you can continue working in that area. Lot of scope is there, lot of research opportunities are there in each one of them. Okay, fine. Now if I consider a general speech processing system, now let us say I am building a speaker identification system or maybe language identification system. So this will be the general block diagram of the system, where there is a speech signal, speech sample. First, we will give it to a feature extractor, which will extract some features from the speech sample, which will be in the form of set of vectors, sequence of feature vectors we call. And that sequence of feature vectors are then given to the backend classifier. So this classifier can be any machine learning classifier which you studied in machine learning or maybe in deep learning. Like it can be your SVM, support vector machine, or it can be KNN, K nearest neighbor classifier, or you can use some deep learning based backend classifier also. So that classifier will identify the class of the speech sample. So in case of speaker ID, it will come up with identity of the speaker. In case of language ID, it will come up with which language is present in the speech sample. Okay. Now, I told you that this is the incoming speech sample and we are giving it to the feature extractor, and then we are giving it to the set of feature vectors we are giving to the classifier. Now, why this feature extractor is required here? Why not we simply feed this speech sample to the classifier directly? Any answers on it? Any guess? Is the question clear? My question is, there is a speech sample. We pass it to the feature extractor. It will give you set of feature vectors, and then that set of feature vector is given to the classifier, which will classify this speech sample into the class, n number of class, any one it will select. Question is, why is that feature extractor required? Why can't we feed the speech sample directly to the classifier?
Sir, a certain speech contains its speech, its amplitude, its loudness. So we have to divide it in that features. Then we put it into the classes. So that's why the feature extractor is needed.
Okay, any other answers? Hope the question is clear at least. basically, if you consider the speech sample, it is a digitized form of signal. The actual speech signal is analog in nature, but in computers, when you're storing, you're taking samples of that and you are doing quantization. And for every bit, you'll use some 16-bit representation or 32-bit representation, depending on the type of representation. So huge amount of memory is required to store the given speech sample entire. Okay, that is one thing. Now, second thing, if the purpose of the if our purpose is to identify only language, then it is sufficient only for us only extract the language specific contents in the speech. I told you that given a speech sample, so many informations are hidden in that. So many information is hidden in that given speech sample. But what we need is only language specific content. If our interest is to find the language of the speech. Okay? So if our intention is to find only emotion in the speech, then we can throw the rest of the information. We will extract only emotion specific feature. Whether we will be able to differentiate between them or not, that is a different question. I'll come to that later. But is the logic clear? Whatever is needed to us, only that information we will keep and remaining we will discard. So that is actually feature extraction. Okay. So because of feature extraction, we are actually saving some memory. We are not, there is no need to save the entire speech sample. We are just storing some set of vectors which are required for our purpose. Okay. So that set of feature vectors is then given to the classifier, which will come up with the class label. Okay. Right. Now, so in order to understand the speech processing and the signal processing requirement for the speech speech processing, we should understand how speech signal is actually produced in a human being. The speech production mechanism that we need to understand. Okay? Now, in a human being, the speech is produced by combined action of lungs, vocal cords, and vocal tract. Okay, 3 parts: lungs, vocal cord, and vocal tract. Now, lungs in the speech production, lungs, it acts as a source of power supply. It actually produces a constant flow of air through vocal cord and vocal tract. That air gets modulated by vocal cord and vocal tract to produce the sound. Now, whenever you are speaking, you can just keep your hand in front of your mouth and you can feel that air is actually coming out of your mouth or maybe nose during the speech production. Without that, you cannot produce speech. You can just try it. You can just speak 1 or 2 words and you can feel that air is coming out of your mouth. So that air is actually coming from the lungs, obviously, which is the source of power supply. We take it as the source of power supply for the speech production. Okay. So now lungs produces a constant flow of air which goes to the vocal cords. Now this vocal cord, it is situated in your neck. Okay. So if you just hold your finger in your neck and if you speak, then you can feel that something is vibrating in your inside the neck, right? So which is that vibrating part that is called as vocal cord. Can you feel that? You can just produce some voiced speech, like you can say ah or oo. That is also sufficient, or you can speak 1 or 2 words. You can feel that the vocal cords are actually vibrating during the speech production. So job of the vocal cord, so this is actually the vocal cord which is situated in your neck. So job of the vocal cord is that it will modulate the output from the lungs. So lungs is actually producing a constant flow of air. Now this vocal cord will convert that constant flow of air into a periodic pulses of air, something like this. So this vocal cord will actually close and open periodically to produce periodic pulses of air. So whenever vocal cords are closed, there is no air flow. So it is 0 here, you can see. Whenever it is opening, the airflow starts increasing and it reaches maximum. And when it is closing, that is the return phase, we call it as return phase, returning back to 0, closed state. So again, the airflow decreases and finally becomes 0. So this thing actually repeats, this operation actually repeats, producing a periodic pulses of air. Okay, so whatever you get at the output of the vocal cord is this periodic pulses of air. The time taken to complete one period of this vocal cord, that is actually known as glottal cycle, that is known as the time taken to complete one cycle is called pitch period. And inverse of pitch period, that is 1 by pitch period, that gives you the pitch frequency, or simply pitch. Pitch of the speech is the rate at which vocal cord vibrates when you are speaking. So, as I told you, this vocal cord periodically closes and opens. Therefore, the size and shape and mass of the vocal cord plays a role in pitch period or in pitch frequency. If the vocal cords are heavier, then it will take more time for it to complete one cycle. If it is lighter, if the weight is less, then it will vibrate more frequently. So that is the reason why male pitch frequency is less compared to female pitch frequency and the child pitch frequency. In adult males, the vocal cords will be thick and heavy compared to females. Therefore, it will open and close slowly because it is more heavier. Therefore, the pitch period is more, time taken to complete one cycle is more. Because of that, the pitch frequency is less for adult male. The range of pitch frequency will be around 80 Hertz to 150 or 160 Hertz. And for female, typically the pitch frequency is between 150 to 250 or maybe 300 Hertz. Okay, it depends on the person to person if there is a variation, but in general, male will have less pitch frequency, female will have higher pitch frequency, and for child, the vocal cords are very lighter, therefore it can vibrate very fast, right? Because of that, the pitch frequency is very high. The pitch frequency is usually around 300 or more than 300 Hertz for child. So just by looking at, finding the pitch frequency, you can differentiate between male voice, female voice, and child voice. Is it okay? Any questions you want to ask at this moment?
No, sir.
Is the concept clear?
Yes.
So now I told
Yes,
you that the vocal cords is actually converting the constant flow of air from the lungs into periodic pulses of air. That periodic pulses of air gets resonated inside the vocal tract. Now, what is vocal tract? Vocal tract is the, simply you can take it as the cavity present within our mouth and nose, as well as the cavity present in the neck. All this cavity together, we call it as vocal tract. Vocal cord is situated in neck, which is vibrating during the speech production. Vocal tract is the cavity present inside nose and mouth, simply. Okay. So now what happens? The output of the vocal cord, which is periodic pulses of air, when it passes through the cavity within the nose and mouth, it gets resonated. It's something like we are playing the flute, Murali, playing the flute. So in flute, what is happening? You're actually pushing the air through that cavity of that flute. The air gets resonated inside the flute, producing the sound. So if you're just closing some holes and opening some other holes, the resonating area inside the flute changes. Because of that, resonating frequency changes. Because of that, the sound changes. That is how we get different sounds from the flute. Similar thing happens in speech production also within our mouth. Different size and shape of the vocal tract, different size and shape of the cavity produces different resonating area, that is resonating frequency, leading to different sound. Okay, and because of the same reason, when a person is having cold, the nasal cavity is usually blocked, isn't it? The resonating area changes. Compared to his normal voice, the resonating frequency changes during when a person is having cold. Because of that, you feel that difference in his voice. Am I clear? Is it okay?
Yes, sir.
Yes.
Yes.
So vocal tract means the cavity inside the nose and mouth, and also your tongue is playing a role in that, and your jaw is continuously moving in producing different size and shape of the vocal tract, hence producing different sound. So this is how speech is actually produced in human being. We are trained from right from our childhood to produce different sounds, and that is why we are able to produce speech. Okay. Now, different size and shape of the vocal tract produces different sound, and if I plot those sounds in time domain, I'll get waveforms something like this. This is speech signal plotted in time domain for very short duration, maybe around 20 milliseconds or so. So the top one waveform here, this is the waveform corresponding to sound ah. If I pronounce ah, this is how the time domain waveforms will look like. Second one is E. If I pronounce E, then the second waveform you will get. And if I pronounce oo, then the third waveform you will get in time domain. Okay. Why? Because when we can just test it. When you are pronouncing ah and when you are pronouncing E, the size and shape of the vocal tract is different, isn't it? The position of the tongue and the position of the jaw is different. Because of that, the resonating frequency of the speech is different, and you are getting different sound there. Okay. So same thing in frequency domain. If I plot, this is the time domain waveform, what I have on the green, that is the time domain waveform, amplitude versus time. And on the right side, whatever I'm having, that is the frequency domain representation. How do I get the frequency domain representation of a signal?
By using Fourier transform.
Yes, by taking the Fourier transformation. So when I take the Fourier transformation of the first signal, I will get a spectrum something like this. So this is the spectrum of A, and second one is spectrum of E, and that is third one is spectrum of U. You can see that the spectrum is different, which means that the frequency contents and their energy is different in different sounds. Spectrum basically gives you the strength of different frequency components in a signal, right? So all these images I have taken from internet. So I have given that in my reference. Okay, these are not generated by me. Now, as I have mentioned, different sounds have different waveforms, both in time domain as well as in frequency domain, which are due to action of the vocal tract. Okay. So now, for our signal processing purposes, usually this speech production operation is taken as a source filter model, where source is the input signal which is coming out of the vocal cords, and the vocal tract is something which is modulating that input. We consider that as a filter, a linear time invariant system, LTI system. The input signal is modulated or processed by this filter, which is the vocal tract, to produce the output speech signal. Okay, so this is the source filter model. Now, as I have mentioned, the output of the speech signal, that depends on the characteristic of the vocal tract. So size and shape of the vocal tract decides what is the speech sound which is coming out. The output depends on the characteristic of vocal tract. Right? This characteristics of the vocal tract, that depends on several factors, isn't it? So what are the factors on which the vocal tract parameters can depend? What are the parameters? What are the characteristic on which the vocal tract parameter will depend? First thing, it depends on what we are speaking. As I mentioned, A versus E, when I say, the size and shape of the vocal tract is different, right? Second thing, it depends on who is speaking. The output speech, what is coming out, that has some characteristic of the speaker. Just by listening to speech, we can identify who is this person, who is the speaker. Therefore, obviously, it has some content related to the speaker. Third thing is the health issue. If a person is having health issue, that also affects the speech, right? Therefore, whatever feature we are trying to extract from the speech signal, it should represent the properties of the vocal tract to some extent. Am I clear? If I am trying to understand, if I am trying to identify who is speaking, then the feature vector used in the process, that should actually represent speaker related information in the speech. If I am trying to extract what the person is speaking, then the extracted feature should represent the content which is actually producing that sound. And also, if it is voice pathology we are doing, then it should represent the health related issue which is actually affecting the speech. Okay. Now, a general frequency representation, feature representation used in speech processing is actually null frequency capsular coefficient, or MFCC. Have you heard about MFCC? Anyone? MFCC features?
No, sir.
Okay.
No,
So, no problem. I'll just explain that. So MFCC, or null frequency capsule coefficient, is the commonly used feature vector in most of the speech processing applications. It does not mean that there are no other type of feature vectors or feature extraction method. There are other type of feature extraction methods, but common thing is MFCC for most of the basic applications, and that is sufficient actually. To understand what is MFCC and how it is actually capturing the characteristics of the vocal tract, we should first understand the human hearing system, because this MFCC tries to mimic the human hearing system. Okay. So this figure shows the human ear. Now, incoming speech signal, which I told you that it is an acoustic waveform, is now captured by this outer ear here, and that makes the audio waveform to pass through this auditory canal. Okay. So the acoustic waveform, which is speech signal or any other noise, acoustic noise, when it passes through this auditory canal, it hits that eardrum. This is the eardrum. So when it hits the eardrum starts vibrating, where amplitude and frequency of the vibration depends on amplitude and frequency of the incoming signal. This vibration of the eardrum is then passed to something called as inner ear or cochlea. A cochlea is the inner ear, which is this semicircular or circular thing which is situated here. Okay. So the incoming audio signal or speech signal hits the eardrum. Eardrum starts vibrating. Because of that vibration, this inner ear also starts vibrating. That gets that energy from the eardrum. The inner ear or cochlea speciality is that it has some around 20,000 hair cells, tiny hair cells situated in the inner wall of cochlea. Okay. Speciality of that the hair cell present in the inner wall is that a set of hair cell, each hair cell or a given set of hair cell will vibrate at maximum amplitude only for a given range of frequencies. That means if there are 20,000 hair cells, maybe first set of hair cell, it will vibrate only for incoming signal, which is having frequency from 20 hertz to 50 hertz. If the incoming signal is having 20 hertz to 50 hertz, first set of hair cell will be vibrating. No other hair cell set will be vibrating, or maybe at least it is not vibrating at the maximum amplitude. If the incoming signal is having frequency between 40 to 80 hertz, then the second set of hair cell will vibrate. And if it is between 80 to 120, then third set of hair cell will vibrate. Okay, so it is like that. So each hair cell or given set of hair cell will vibrate at maximum amplitude only for a given particular frequency or range of frequency. These vibrations actually causes production of tiny voltage pulses, which are then sensed by the auditory nerves, and it is sent to the brain. Okay? So it is something like this. Now let us say there is an incoming sound ah, whose spectrum is given in this pink or red color, and there is an incoming signal E, one more speech sample, whose spectrum is given in this blue color. So this is that inner ear, cochlea, the same circular thing which I showed in this figure, this part, zoomed version of that. So when sound ah is pronounced, this is the just stretched version of this inner ear. So here it is circular. If I just stretch it, it will look something like this below here. So when I pronounce ah, then these set of hair cells will vibrate within that inner ear. These set of hair cells will vibrate. And when I pronounce E, then these set of hair cells will vibrate, which are actually different from the hair cells which will vibrate for ah, because the frequency contents are different. Okay. Now you can clearly see the difference between the set of hair cells which are actually producing the output for ah are different than the set of hair cells which will produce output for E. Right? Each of these hair cells are connected to brain through these nerves. That means the voltage signal which is going to the brain is different for A and it is different for E. Using this nerve signal, brain differentiates between, or brain understands that, okay, if this is the incoming pattern, then it must be A. If this is the incoming pattern, then it must be E. Right? So this is how brain understands what is the incoming signal. Is it okay?
Yes.
Right. So how does the actually brain understand that it is A and E? It is basically due to the training that is given to the brain. Right from our childhood, we are trained to do so. A small baby of 3 months or maybe 6 months will teach the baby few words like amma, appa. So that simple words will teach the baby. So that word gets registered into baby's brain, and as baby grows, more and more words are registered in the brain. So it already knows, the brain already knows, okay, if this is the incoming pattern, then this is the word amma. If this is the incoming pattern, then this is the word tree, something like that. Okay, so that is how the brain understands, and actually brain performs the pattern recognition, incoming signal pattern recognition, right? Now, the operation of the ear, which I mentioned here, that different set of hair cell vibrate for different frequency. So that can be modeled as a filter bank. Filter bank means you must have studied low pass filters, high pass filters, and band pass filters. So this operation, I can treat it as a set of bandpass filters placed together, where different hair cell, set of hair cell is equated to different filters, bandpass filters. That means if this incoming signal is having frequency from 20 to 40 hertz, then first bandpass filter will produce the output. If the signal is having 40 to 80 hertz, second bandpass filter will produce the output. And then if it is from 80 to 120, third bandpass filter will produce the output. Right. So it is a bank of filters or filter bank representation.
Sir, can you show
Now,
the previous page?
sorry.
Can you show the previous page? Sir,
Yes,
here
madam.
the different patterns you are talking about, the pattern is seen in the hair cell.
Yes, yes.
Okay, sir.
So this is the inner ear, which is actually present in our inside the ear, cochlea. If I just stretch that inner ear, this is how it will look like. And these white things here, they are the hair cells. It is just a pictorial representation. Actually, it will look different. I mean, this is how it works.
Yes, sir.
Now, I told you that different set of hairs will vibrate for different frequencies. And the interesting fact here is that the bandwidth of these filters increases with increase in frequency. In other words, we say that it follows something called as Mel scale. Okay, we'll see what is that Mel scale. So if I model the bandwidth of a bandpass filter, which is present inside our ear as a bandpass filter, now the frequency response of that filter is actually found to be kind of triangular representation. I mean, triangular frequency, passband frequency, frequency response of the filter. Okay. Now, if you consider this, just for your understanding, if the first one, if you take it as the frequency response of the first bandpass filter, the second one is the frequency response of the second filter, third filter, fourth filter, fifth filter, so on. You see that when there is an increase in frequency, the bandwidth increases, right? This filter, if you see here, it is having very small bandwidth. It is maybe from 1500 hertz to 2500 hertz, but here it is from 5000 hertz to 8000 hertz. Okay, so it is practically proven that human ear sensitivity for frequency is very high at low frequency, and human hearing sensitivity for frequency is low at higher frequency. High sensitivity at low frequency and low sensitivity at high frequency. For your better understanding, I'll just give you an example. Let us say there is an incoming speech signal or audio signal of 100 hertz. And if I change the frequency from 100 hertz to 110 hertz, I will quickly understand that there is a change in frequency because the sound changes. Okay, 100 to 110 hertz when I change, I will understand that there is a change in frequency. But if I consider a signal which is having 10,000 hertz as the frequency, 10 kilohertz, and if I change that frequency from 10 kilo to 10,000 plus 10 hertz, that is 10,010 hertz, I will not observe that change in frequency. Am I clear? From 100 to 110 when I change, I will understand that there is a change in frequency. Same 10 hertz change if I do at a higher frequency range, that is 10,000 hertz to 10,010 hertz if I do, then I will not observe that change in frequency. To observe that change in frequency, I may have to change it by some 100 hertz or 200 hertz, maybe 10,000 and 100 or 10,200 hertz when I change. In that case, I will understand that, okay, there is a change in frequency of the incoming signal. Why that happens? It is from the same filter bank representation. See, when I change from if I consider the 100 hertz scenario, maybe this second filter is giving you the output for 100 hertz. If I change the frequency from 100 to 110 hertz, instead of second filter, third filter will start giving you the output. Okay, so because of that, in this diagram, instead of this second, third hair cell, fourth one will start vibrating. For 100 hertz, third one will vibrate. For 110, fourth one will vibrate. So brain will understand, okay, the signal is coming from fourth one, so there is a change in frequency. But at higher frequency, 10,000 hertz as well as 10,010 hertz, both are corresponding to same set of hair cells. There is the output from which the signal is coming, there is no change. Okay, in order to observe that change, maybe you'll have to change the frequency by 200 hertz or so, where there will be change in set of hair cells. In that case, brain will understand that, okay, there is a change in frequency. Is it okay? So we say that the human hearing sensitivity follows something called as MEL scale. Okay? It's called as MEL scale. The commonly used feature representation, that is MEL frequency cepstral coefficient, or MFCC, it mimics this human hearing system. It tries to mimic that human hearing. So this figure shows the steps used in MEL frequency cepstral coefficient computation, MFCC computation. So your first step is that this is the incoming speech signal, that you divide it into small frames, small segments. Each segment may be around 25 or 30 milliseconds. Then for each frame, we'll take the Fourier transformation, discrete Fourier transformation, that is DFT. You'll get the spectrum of the signal. On the spectrum, we'll perform this MEL frequency wrapping to mimic the human hearing system. So we get something called as MEL spectrum. So the spectrum what we have here, that will have the frequency axis linearly. It is in hertz. Spectrum what you get, the frequency axis is linear. And for this one, we are doing the MEL frequency wrapping. Okay, and on that, we are performing some log operation on the amplitude. Log of the MEL spectrum we take, and then you take inverse Fourier transformation of that, whatever is the result of this log operation. Or you can take discrete cosine transformation also. In fact, they are similar in fact. Okay, so output of that, whatever you get, the set of coefficients, set of numbers, that is known as MEL frequency cepstral coefficient. Usually for each frame, you will get a 12-dimensional vector or maybe 13-dimensional vector. That is the MFCC vector. Okay. Now I told you that first step is to convert the speech signal into frame, which is carrying a duration of maybe 25 milliseconds or 30 milliseconds. In almost every speech processing application, we perform this framing. We divide the speech signal into segments, small segments of 25 milliseconds or maybe 30 milliseconds, depending on the application. Why that framing is required? Any idea? And first of all, how do you get that frame? The speech signal is actually multiplied by windows. You might have heard Hamming window, Hanning window. How many of you studied digital signal processing? Did you hear Hamming window, Hanning window and all? Did you study Hamming window, Hanning window, or any windowing technique in digital signal processing or maybe signals and system?
Yes, sir.
So this frame what you get here is actually multiplying the signal by the window. In this case, you can take a rectangular window, so no problem. Question is why this windowing is required? Why do we need to take only small segment of this page? Why not entire speech? Answer is, if you consider the entire speech signal, the properties of the speech signal within this duration, it changes very significantly. Properties in the sense mean and variance, if you consider the values, it will change significantly. Initially, mean is 0. I mean, This amplitude is very small here. Here the amplitude is increasing. Here it is increasing more, and again it is decreasing, and so on. If you just zoom in and see, you will understand that. But whatever analysis we are doing in signal processing, that is under the assumption that the signal is stationary, or at least wide sense stationary. So if the properties are changing too much, then whatever whatever processing we are doing, that may not be accurate. In other words, if I take only a small segment of the speech sample, which is maybe around 25 or 30 milliseconds, within that duration, the properties of the speech remain almost constant. You can see that in this figure. This is kind of a periodic waveform, which is periodic within that short segment. So here we assume that the signal is stationary, or maybe just wide sense stationary. So all this stationarity, all those things comes in mathematics, probability. Okay. So you take the Fourier transformation of that, discrete Fourier transformation of that, then you get the spectrum. Then you do all these steps, you'll get the MFCC vector. For each frame, you get a 12 or 13 dimension MFCC. So this MFCC vector is actually a representation, compact representation of the speech present within 25 or 30 milliseconds, right? So for the next frame also, you will get MFCC vector. The third one also, you'll get MFCC vector, so on. So for the entire speech signal, maybe you'll get some 100 MFCC vectors, or maybe some 200 MFCC vectors, depending on the length of the speech sample. Okay, so this is how the MFCC is actually capturing the information. If I consider the spectrum of a speech, whatever I have shown here, this is the small segment of the speech here. If I take the spectrum, that is the Fourier transformation, I get the spectrum. That spectrum will look something like this. Okay, these are the different frequency components present in there. When I do null frequency wrapping, actually I'm trying to identify what is the amount of energy present within each triangular filter. This is actually mimicking our human hearing, because there also we are trying to find how much is the energy present within each frequency band, because each hair cell, set of hair cell, is corresponding to a range of frequencies. Similar thing we are doing in this calculation of MFCC. So that's why we say that MFCC actually mimicking the human hearing system. So coming back to the general speech processing system block diagram again. So now we know why this feature extraction is required. This is the incoming speech sample. Let us say this is the MFCC feature extraction. We get a set of vectors or sequence of vectors of MFCC that is given to the classifier, backend classifier, which will classify the speech into one class. If it is speaker identification, it will identify the speaker. If it is language identification, it will identify the language. Now, as I told you, each MFCC vector, it contains the information for around 25 millisecond or 30 millisecond. But if you consider only 25 millisecond, it is very difficult to identify the language or speaker within just duration of 25 millisecond. 25 millisecond is very small, right? Whatever you say, one word will approximately take 1 second. Okay, so 25 millisecond is very small fraction of that. Within that, you cannot identify the language or speaker. Of course, we are considering the sequence of feature vectors, but then individual MFCC vectors are not carrying long context in the sense, the time in duration I'm saying here. So also, in this case, this set of MFCC, whatever I'm getting, each MFCC is representing only 25 milliseconds, and it is not representing how the speech is varying from this frame to next frame. So that information is also required for us. Sequence, see, speech is a sequential thing. That sequence matters a lot in case of speech signal. How this feature vector is varying from this frame to next frame to the another next frame, like that. Okay. To model that, there is something called as delta MFCC. In delta MFCC, what we do is that we consider this frame, we take the difference between previous one and next one, then we append that difference below this. Okay, if it is 12-dimensional MFCC, this is also 12-dimensional, this is also 12-dimensional, two vectors, we take the difference between them. When you take the difference between them, it indicates how the MFCC varying from previous vector to next vector. So that information is captured there. So that difference will append to the current frame. So that becomes 12-dimensional plus 12-dimensional, which is below that, that becomes 24-dimensional. And we represent it here, the delta MFCC. Okay. So along with delta MFCC, sometimes we take delta MFCC, that is second order difference also we take. So in that case, we consider 2 frames before this and 2 frames next to that. So then that gives you some more information how the feature vectors are varying from this frame to next frame and next frame to next frame, right? So that dynamic information, dynamic variation is captured in the delta and double delta. Double delta is delta MFCC. 2 times we take difference. Okay. Now, one simple application, if I consider, let us say I'm going to perform language IT, where we are trying to identify the spoken language in the given speech sample. So usual procedure is that I will have a training database. Let us say I want to identify Odia, Hindi, and English. 3 languages are there in my database. So I have some 100 samples from Odia language, different sentences spoken, maybe 100 or 150 samples from Hindi, and maybe some 100 or something samples from English. So maybe from different speakers. Actually, it has to be from different speakers for better generalization. So for each speech signal, which I call as the training data set, I will do the feature extraction. In this case, I can do MFCC along with delta and double delta. I'll get, for each sample, I'll get a sequence of feature vectors. I will use them to build a classifier. So 3 classes of MFCC vectors I'm having, actually 3 classes of features I'm having. So this is class 1, class 2, and class 3. When I plot them in the 2-dimensional, they may cluster together. All the feature vectors or all the samples from class 1 they will form a cluster usually. This is class 2, they will form a cluster, something like this. And this class 3, maybe Odia, Hindi, and English in this case you can consider. So that is during the training phase. Now during the testing phase, there will be a test sample. Again, I will do the feature extraction for that feature vector. Or if I just take the if I take the test sample and do the feature extraction, and I see that test sample will be somewhere here, let us say, just for example. Okay. Now we will compare this test sample with the class 1, class 2, and class 3. And we see that in this case, this test sample is very close to class 1, right? So we'll identify that, or we'll assume that this test sample is belonging to class 1. So this is how we perform classification in case of speech sample. Now remember, when we are doing the feature extraction, like MFCC, I told you that we are dividing the incoming speech sample into multiple frames, and for each frame we are computing the MFCC vector. That means number of feature vectors what we get for a speech sample, that depends on the duration of the speech sample. If I just say KIIT, that is just one word, and maybe it is hardly 1 second or 2 second speech sample I am giving you. And if I give you a bigger sentence, like this workshop is organized by KIIT, so that is also English only. The earlier sample also, what I pronounced is a sample from English language. Second is the entire sentence. This workshop is organized by KIIT. That is also a sample from English language, but its duration is more, right? It will take more time because more number of words were there. The number of feature vectors what we get for the second sample is significantly larger because the duration is more, right? Maybe for the second sample, you are getting some 500 frames. For the first one, you are getting only 100 frames, but both are belonging to English one, right? So how do you model them? One crude way is to take the average of all these things, okay? Irrespective of whether it is 100 frames or 500 frames or 400 frames, when you take the average, you will get only one frame. That is only one vector. So entire speech sample is represented by only one vector. So that's very crude way. I'm just saying that that's crude way because there are better ways of modeling that, which you will study in deep learning or maybe in machine learning courses. Okay. So because we cannot feed that varying length speech to the backend classifier directly. So that you should also remember. Okay. So that's all I wanted to cover. I have given you some basics of speech processing, some applications of that, what are the different research areas in speech processing. So, and MFCC also I have explained you. So at this moment, that is fine. That much is sufficient for your understanding. Thank you. So if you have any questions, you can ask me.
Thank you, Dr. MuraliKrishnan. Anyone having any questions? Kindly free to ask to sir. Yes, Kuldeep, have you any question?
Excuse me, sir.
Yes,
Yes,
Sunali.
madam.
Sir, how are these MFCs calculated? Can you please tell me in brief?
MFCC calculation?
Yes, sir. That Fourier transformation you have said.
I mean, you are asking how it is
Yes, sir.
computed practically? Or,
Yes, sir, practically.
so if you see Python, there is a library called Librosa.
Okay. Libro?
Librosa.
Okay.
Librosa. In that Librosa, you will have to install Librosa.
Okay.
Speech process, audio processing. In that, there is a function called MFCC. So librosa.mfcc will give you the MFCC features. It will internally do all these operations.
Okay.
Okay. There may be other libraries, but Librosa is the commonly used library for speech and audio processing application.
Okay.
Did
Sir.
I answer your question? This
Yes,
was
sir.
the thing you are asking, right?
Sir, it will calculate all the frequency.
It will internally do all those things. See, steps are shown here. First,
Okay.
speech signal is converted into frames using windowing technique. Then for each frame, you will take the Fourier transformation, DFT, that will give you the spectrum. Then you will perform L frequency wrapping to mimic the human hearing system. Then you will do, you will take the logarithm of the amplitude. Then you will take the inverse Fourier transformation or discrete cosine transformation. That gives you the MFCC. This entire operation is actually done by that single function, librosa.mfcc.
Sir, how will this work if there is a multiple noise signal or if there are many speakers? Sorry,
now
sir.
Here, see, whatever feature extraction we are doing,
Yes,
that
sir.
feature extraction does not consider whether there is speech from multiple speakers or there is noise. Anything it does not consider. It does just does this operation. If you feed noise signal also, there also you will get MFCC vector. But what is the meaning of that MFCC vector? That we will have to see. That is left to the expert, subject expert. Human intelligence is required in that case. Because MFCC function does not understand whether it is a speech, whether it's a speech from single speaker, or whether it is a speech from multiple speaker, or there is a noise. So all those things it does not consider it. Simply performs these predefined operations to get this MFCC vector. So if there is a noise, then you'll have to do some pre-processing to remove that noise, if it is possible to remove that noise, or if not, you'll have to do some post-processing technique where after feature extraction also you can suppress the effect of noise to some extent. You might have heard autoencoders in deep
Yes,
learning.
sir.
So you can use autoencoders to suppress the effect of noise if you train it properly.
Anyone else having any questions? I think no one. Okay. So if anyone interested to start work on this or anyone
Excuse me,
interested.
sir.
Yes, Akida, yes.
Sir, someone has asked a question in the chat box.
Yes, I will look into that. Google
Sir,
Assistant
yes.
Cortana uses this technology. Yes, they use this technology. Good point. See, one more point here. See, question was, does Google Assistant, Siri, Cortana, Alexa uses this technology? Answer is yes. They are using automatic speech recognition. But there is one more thing. Right now, the current technology is that if you just look into this Alexa or Google Assistant, whatever you are speaking during the voice search, it will try to decode in the predefined language only. For example, if you say in English, it will understand. And in between, if you suddenly switch to Odia, it will try to decode that in Odia only. It will not switch to Odia because Alexa or Google Assistant does not understand Odia. Right? So this is one research problem which is currently going on. That is now actually known as language diarization, where you need to identify the change in language, at what point the language is switching, and then load the appropriate language model there. Half of the sentence you are speaking in English, and suddenly remaining half you will speak in Odia. Right? So when there is no proper technology, then the Google Assistant or Alexa, it will try to decode the entire thing in English only, which is not correct. Okay, so as I told you, the lot of work has been already done in speech processing different areas, but still lot of works are still pending. There are so many research problems are still open.
Any other questions? I think no.
Sir, can you please explain the MFCC delta again?
Yes. So whatever
Is
operation
it
we are
just a
doing,
second order differential or is it something else?
it is second order differential. First one is delta MFCC. What
Yes,
you do
sir.
here is delta MFCC. For the current frame, if I consider this third one as the current frame, I'll take the difference between, this is n minus 1 and n plus 1. I'll consider these two and I'll take the difference between them, n minus 1 and n plus 1. So this is a vector of 12 dimension. This is also a vector of 12 dimension. This is also a vector of 12 dimension. So when I take the difference between these two, n minus 1 and n plus 1 vector, again I will get a vector of 12 dimension. That vector, difference vector, I usually append to the nth MFCC vector. So it becomes 12 dimensional original MFCC followed by 12 dimensional delta MFCC, the difference vector. So that makes it 24 dimensional vector. Okay. Similar thing, this is just first order difference. So I call it as delta MFCC. Second order difference also I can consider, or nth order difference also I consider, but usually up to second order only we go. What is the advantage? So how the speech is varying from this frame to this frame. So that information is now captured. That gives you slightly more context on the speech signal, which is better because speech is sequential information. It's carrying sequential information.
Any other questions? Okay, I think no. So anyone interested to be in touch with Dr. MuraliKrishna can contact with me, or directly you can contact to Murali sir. So thank you, Murali sir. With a very short notice, you were accepted and given a very nice talk. And definitely, I hope our collaboration will be there in future. And if anyone will contact with me, definitely we'll start some group and do some work on this. And thank you very much once again.
Thank you, sir. Thank you, Satyaran.
Thank you. Thank you, sir. Namaste.